Okay, moving right along to the next example. If you've never paid attention, if you toss something up in the air, it's going to go through three different motions, right? Or three different pieces, right? It's going to slow down as it's traveling upwards. Okay? At some point, it's going to stop and turn around, right? It'll stop in the air and then immediately turn around and start falling back towards the ground. Okay? When it stops, that is when it has reached its maximum height. That is the point where it is going to be as high up off the ground as it's going to go. Right? If you're throwing out, the faster you throw it, the higher it goes. As it falls back to the ground, right, it's going to speed up. It's going to go faster and faster and faster. It's going to accelerate towards the ground. In fact, it's always accelerating towards the ground as soon as you release it. Right? Because the acceleration is constant, it's always pointing downwards towards the earth, no matter which direction you throw the ball. Then we can consider each part of these as independent motions, right? That constant acceleration never changes, and so we can break this up into pieces. And this is important when we deal with motion, not just in one dimension, but as you'll see in a few minutes, in two dimensions. It's important to be able to break these motions up and consider them separately. So let's try an example like this. We have a toy rocket that uses fireworks to launch itself straight into the air at 25 meters per second. Okay, if we neglect air resistance, we want to find these values. So what's going to happen is the rocket's going to launch straight into the air at 25 meters per second. It's going to go up, it's going to reach some point, and then it's going to turn back around and fall back to the ground. And it's going to end where it started from. Now, this point where it reaches is the maximum height. And that's what we want to find. Okay, but in this case, right, it's really delta x, or the distance that this ball is going to travel, or the toy rocket's going to travel. So if we want to find the maximum height, then we just need to know some of the other parts of the equations to figure out which one we need. So we know that the initial velocity, 25 meters per second. When it reaches the top here and stops and turns around, anytime something stops, the velocity is 0. And so the final velocity here at the top of its motion, so halfway through its entire motion, and we know the acceleration. Now you don't use this equation much, okay, but we can use it here. Vf squared equals Vi squared plus 2 times A times delta x. And this is the component that we're looking for. And we know everything else. Final velocity is 0. The initial velocity is 25 squared. Okay, 25 squared is 625. Plus 2 times negative 9.8 times delta x. And so that should give you, I think it's 19.6, negative 19.6. There's delta x. Again, we just want to solve this. Subtract 625 from both sides. And we'll get negative 625 divided by negative 19.6 equals delta x. And that should give you 31.89 or 31.9 meters. And so if you throw an object up at 25 meters per second, it'll travel about 30 meters into the air. And before it stops, turns back around, and comes back down. And so now that we know this, right, what's the speed of the rocket when it reaches the maximum height? Well, we already figured that out. The speed and velocity when it reaches that point is going to be 0. So how much time does it take for it to reach the maximum height? Well, we can figure that out using a different equation. It's actually a little bit easier VF equals VI plus a delta t. And you know which equation to use because you're always going to be missing one thing and have everything else, right? So we have the initial and final velocity for our motion here. We have the acceleration. We just don't have time. And honestly, you could do, in this type of question, you could do part B before you do part A. And in that case, it actually makes it maybe a little bit easier mathematically. So the final velocity when it reaches its maximum height is 0. The initial velocity is 25 meters upwards, or 25 meters per second upwards. The acceleration is negative 9.8 because it always points downwards, times delta t. Subtract 25 from both sides. And then if we divide by negative 9.8, you'll find that the time is equal to 2.55 seconds. Okay, that's it. Seconds. So now we have the time that it takes for it to reach its maximum height. Let's take a look at the next part. How long does it take to fall from its maximum height back down to the ground, right? So for the whole thing we've done so far, we've been talking about the first part of the motion, right? It starts at the bottom at 25 meters per second, travels straight upwards till it reaches the maximum height where the velocity is 0. Now we want to talk about the second half. How long does it take for the rocket to fall from its maximum height back to the ground? Well, if we want to figure out how long it takes for it to fall back to the ground, right, then we need the time. To find the time, we're going to want to use the equation delta x equals VI delta t plus 1/2 a delta t squared. Now, because we're talking about the second part of the motion, our initial velocity is different. Here, from the top to the bottom as it's falling, right, it starts with no initial velocity, so this is 0. And then it's going to be speeding up until it reaches some final velocity on the ground. Okay, and so if we want to find the time that it takes for the ball to reach the ground or the rocket from its maximum height, well, we know from before that delta x is 31.89 meters. It goes up by 31.89 meters. Okay, so that means it has to fall down that far. And so when it falls down, negative 31.89 meters, it's equal to 1/2 times negative 9.8, the acceleration due to gravity, times delta t squared. If we then simplify this just a little bit and then divide, this is negative 4.9 times t squared. If we divide by negative 4.9 on both sides, we get t squared equals, I didn't write that part down, but what you wind up with, let's just see what that's going to be real quick, you guys. I tried to do most of the calculations before I started recording so that you wouldn't have to listen to me talk while I was working on a calculator. If we take then the square root of both sides, you're going to get t equals 2.55 seconds. Whoops. So the thing that I definitely want you guys to notice here, and it may seem intuitive, Okay, but it's not really for a lot of people. The time that it takes for it to go upwards is the same time that it takes for it to fall downwards. Okay, this is true for any object that's in motion due to gravity, right? So anytime you throw something up in the air, it takes the same amount of time for it to slow down to 0 as it does for it to speed back up and come back down to the point where it started. So if it starts from the ground and it takes 2.5 seconds to get to the top, it'll take 2.5 seconds to fall back to the ground. If it starts on the ground and it takes 5 seconds to get to the top, it'll take 5 seconds to get to the ground. Because of the constant acceleration due to gravity, that's not the only thing that's the same. Okay, so, well, real quick, the total time, we would just then add these two, right? And you get 5.1 seconds. Wow, I can't write you guys, sorry. Total, 5.1 seconds. Well, what's the velocity, right? And actually, or what's the speed just before it hits the ground? Those are the things that we want to compare. Well, let's look at our, we can still use our kinematic equations, right? The reason why I am showing you all of these examples with these kinematic equations beyond just you guys learning how to do them is to show you that all of the motions that we talk about can be simplified down to these 3 equations. Okay? Sometimes you will see a 4th kinematic equation. It's not as used as often as the other ones. Most textbooks just break them down to 3 now. You won't really need them. Well, you will use them some as we go along. Because they describe motion so well, when we start talking about anything that's moving, we can always reference back to these, so long as that acceleration is constant. And so that's why we talk about them right at the beginning. That's why we talk about motion right at the beginning. Okay, now remember, just before it hits the ground, we're still talking about the second half of the motion. As it's falling from its maximum height, the initial velocity is 0. The acceleration is still negative 9.8. Okay, and the time, 2.55 seconds. That final velocity just before it hits the ground, I would look at the number that I have written down, but I don't really need to. It's going to be negative 25 meters per second. Or the speed, 25 meters per second. Okay? The same speed at which you threw it, or at which the rocket launched. So when it goes straight up in the air, at some particular speed, it's going to be coming down at the exact same speed when it reaches the same height. And so one other way, just to point out how this works, is if you toss something, let's say, off the edge of a building, right? Then if you toss it in the air and it's traveling 25 meters per second from the top of the building, it's going to go up, whatever it is, 2.5 seconds, because it's going to be the same as what we've got here. When it comes back down and reaches this point, okay, now it's 25 meters per second. It's just in the opposite direction. And that's always true for any object tossed in the air if you ignore air resistance. Okay. In the final example, I want to just discuss something with you that I think will be helpful in understanding some of your problems as you're going through the assignments this week. But I'm not sure. We could talk about this for weeks in terms of calculating things. So I don't want to get into a whole bunch of these types of examples right now. I just want to show you how one works, and so that you can kind of understand what's happening when we're analyzing these problems. Whenever you have an object that's moving in 2 dimensions, right? So up and down and left and right, right? If we go back and look, something like this, right? So instead of just throwing it straight up from the top of the building and it coming down, right? We tossed it off the side of the building and it goes at an angle, right? So it travels up and to the right, okay? whenever we talk about those things, right, any motion up or down is going to be influenced by gravity. Gravity is always pulling straight downwards on any object as soon as you release it. But any motion left and right is not influenced by gravity. There's no acceleration to the left or right that's caused by the Earth. If there was, right, you'd be flying into walls all the time. Right? All that gravity does is hold you to the ground. It pulls down, and that's it. And so there's no acceleration left or right. Okay, when we talk about objects that are in motion only under the influence of gravity, things that we throw in the air, right, we call them projectiles. Okay, and so you might see that word going forward in a few weeks. Projectiles will always make a parabolic path in the air. If you ever watch football, you watch them kick a field goal, watch them throw a pass, always a parabola, right? Now, is it a perfect parabola? No, because they're throwing the ball in a particular way. There's air resistance on those things. Okay, but it always generally forms that same kind of U shape. Okay, and that's the parabolic path that we're talking about. The shape of that path depends on the initial velocity. Okay, and it also depends on the air resistance when we're talking about something in real life or non-ideal situations. Okay, if we throw mostly upwards and not to, and less to the right, you'll get a really steep path of motion. Okay, and if you throw mostly to the right, you get a really broad path of motion. And so it completely depends on the initial velocity, how you toss whichever ball it is that you're talking about, right, or object. When we deal with two-dimensional motion, you want to always consider the two dimensions as single, separate dimensions. And you want to connect them by the things that will have to be the same. And so we're going to talk about this example. I don't believe there's an example like this in your practice problems, but there is an example that references parts of this. It references the idea of splitting them up. You don't actually have to do the last problem, and I may kind of save that for you guys because it's taking me a minute here. I may save that for you guys as a bonus because it's a bit tougher than I expected it to be. And for those of you who watch the videos and things, you can get some bonus points by finishing this last problem. But let's talk about the first parts of it. So we have a large boulder that rolls at 12 meters per second horizontally off the edge of a cliff that's 187 meters tall. Okay, and so I believe I mentioned my terrible art skills last week. Okay, but it's going to roll off the edge of the cliff at 12 meters per second. And what happens as soon as it rolls off the edge of the cliff? Well, it starts to travel to the ground. How long does it take for the boulder to reach the ground? Well, once it moves off out from underneath the cliff, right, or without having the cliff underneath it, gravity immediately starts to pull it straight down. And so we can consider the vertical motion of this object without ever talking about the horizontal motion. In other words, if it's traveling at 12 meters per second horizontally, when it comes off the edge of the cliff, its vertical initial velocity is 0. It's starting from rest in the vertical direction, right? And then it'll start to fall at the same time. I believe you'll see in videos or maybe in your textbook or something like that, if you drop an object and push it off the table at the same time, they'll hit the ground at the same time. That's because it takes the same amount of time for it to fall straight down as it does for it to move to the right and fall straight down. Right? Gravity pulls at it the same way, no matter how fast it's traveling horizontally off the edge of the cliff. Could be going 12 meters per second, could be going 120 meters per second. It'll still hit the ground in the same amount of time. To figure out that amount of time, we want to consider, in this case, we'll call it the y direction, okay? Just because we have two directions to talk about. And so the initial velocity in the y direction is 0, right? It's not immediately falling down. It starts falling down when it comes off the cliff, right? We don't know what that final velocity is down here, but we do know how far it has to fall. It has to fall, oh, I'm sorry, we're using y here. It has to fall 187 meters or travel downwards 187 meters. We also know the acceleration to be negative 9.8 meters per second squared. So if we want to figure out the time, we can use the same formula we've been using. I'm just replacing x with y because we're talking about vertical instead of horizontal. Now, I know I used x for the past few examples, even though we were talking about vertical directions. And maybe I should have used y then to make this a little less confusing. It doesn't really matter which letter you use. Okay, if you're talking about one dimension, you can just stick with x. If you're talking about two, x and y. But here I'm just going to use y to keep them separate for you guys. That's going to be vi, the initial y velocity, times delta t, plus 1/2 the y acceleration. All right, remember, there is no acceleration left and right, times delta t squared. Okay, we're looking for the time. Okay, we know delta y is negative 187. We know the initial velocity in the y direction is 0. Okay, and so that's going to be equal to 1/2 times negative 9.8 times t squared. So we're looking for the time. If we then take and divide negative 187 divided by negative 4.9, which is 1/2 times 9.8. That's going to be equal to t squared, right? So we're just going to divide by negative 4.9 on both sides. That'll cancel those out. Oh, negative. And now, once we get that value, we'll take the square root of both sides, and you should get that the time that it takes for the object to fall, delta t, is going to be equal to 6.18 seconds. Let me take the square root of both sides here. And you get t equals, or delta t equals 6.18 seconds. Now, why does time not have a x or y associated with it? Well, the reason for that is the time is the same no matter x or y, right? So that's why we can still break these up into two different motions, right? Into left and right and up and down, because they're linked by time. Right? It only has 6.8 seconds before it hits the ground. And so that's all the time that it has before gravity has pulled it to the ground. So what's going to happen to it in that time, in that 6.18 seconds? Right? Well, it's going to keep traveling to the right for 6.18 seconds. So how far away is it going to move from the cliff? Right? Well, that's the next question. How far from the bottom of the cliff will the boulder land? Right? Or what's the horizontal distance that it travels before it hits the ground? Well, if we want to know the horizontal distance, now we are looking for what we would call delta x. Okay, and I'm just going to redraw this over here real quick so you can kind of see it's going to come off the edge horizontally and land. This is delta x, the thing that we're looking for. How far does it travel horizontally before that 6.8 seconds is up and it hits the ground? Well, we can use the same kinematic equations, except now we need to use the components of the x motion. And the helpful trick here, the helpful trick here is that, remember, we're talking now about horizontal distance, traveling left or right. The acceleration is 0. Nothing is pulling at it left and right, only up, and it's only being pulled down. And so the acceleration 0, it's not going to speed up or slow down left or right. When someone throws a football, right, the football travels at the same speed once they release it. Same thing is true for when they kick a football for a field goal, right? It essentially travels at the same speed once they kick it. Air slows it down a little bit, but it's not speeding up left or right. It might kind of look like it's speeding up or slowing down, but that's because you're seeing it go up and down as well. Right? But as it moves to the right, as it moves towards the goal line, it is always traveling in that same horizontal speed. So the acceleration is 0. And to find the distance that it travels, well, that's just then 12 meters per second. And it's got 6.18 seconds before it hits the ground. If you multiply those two, you find that it will go 74.16 meters before it strikes the ground. And so by breaking up these motions and using time to link them, we can be specific about how long it takes to reach the ground, how far it's going to be, and how far away it's going to be when it reaches the ground. Now, you guys won't get the chance to do this lab, but I used to do a lab with one of my other classes. You guys won't have the stuff to do it, to fire the projectile, essentially, where you can specifically test this. And you can then use it to predict where something is going to land, and works every time within some range. Okay? Things are always, real life situations are not ideal, and there's always little small differences. Right? And so you adjust for that. You couldn't, maybe you can't in real life pinpoint this range down to exactly 74.16 meters. Okay? But you could definitely say it's probably between 65 and 75, between 70 and 80. Right? You could get a range and know that it's going to land at that point without knowing much more about it than just how fast it's traveling. Okay, for this last one, you have to consider, well, I asked what was the velocity. I really should have asked what was the speed here. Okay, but you have to consider two different components. Okay, there's going to be traveling in the x direction at some speed, and it's going to be traveling in the y direction at some speed. Okay, and what we're going to have, if we connect the two, is a nice right triangle. Okay, that red doesn't look so good there. This is VF, the final velocity. Okay. Now, the reason I didn't ask you to find, I should have said speed and not velocity, is because the direction here is not straight up or down, and so it's not just plus or minus. You have to apply an angle and things like that. I'm not going to try to get you to do all that. So find the speed that it's traveling just before it hits the ground. Okay. For anybody who watches the video, makes it this far, we'll just call this a bonus, and you can email it to me. If you try it, I'll give you a couple points. If you get it right, I'll give you a few more points. Okay. This is a little beyond the scope of what I think we should talk about in this class. If we have to revisit it, we'll revisit it another week. And maybe next week I'll show you guys the solution. Okay, but I've shown you today how to solve all of it. The only thing we didn't talk about was adding vectors using the Pythagorean theorem. I believe we did that a little bit last week. Okay, but if not, just remember Pythagorean theorem, when you have a right triangle, a squared plus b squared is equal to c squared. This is how you add vectors. Give this a shot. If you have questions, let me know. But there's just one last thing I want to talk about in terms of things that I think will pop up in your problems this week. When you're considering an object moving, right, the reference frame from which you're looking at the object, right, your frame of reference is really important. Right? If you're driving down the road at 60 miles per hour, someone passes you going 70 miles per hour, to you driving, it's going to look like they're moving at 10 miles per hour. That car compared to your car is moving at 10 miles per hour. Right? If you could see nothing else, right, you can see it moving with respect to the background, so it might look like it's going faster sometimes. Okay, but if all you can see is you and the other car, right, then that car looks like it's going 10 miles per hour. If you're standing on the side of the road, right, that car that appears to be going 10 miles per hour will definitely look like it's traveling 70 then. Right? If you ever, and I hope this never happens to anybody, but if you ever had a breakdown on the side of the interstate, you know that cars look a lot faster when you're not moving. The difference that you experience in this case is based on your frame of reference, right? Whether you are moving while you observe something or whether you're standing still while you observe it. Okay. Yeah. So when you're when the frame of reference is inside the car, right, the car appears to be moving different than when you're outside the car. The reason that I mention this is there is no preferred reference frame in terms of measuring motion. And we maybe could caveat this later, but we're not going to talk about Einstein for a while. Because there's no preferred reference frame, it doesn't matter what you're doing. The motion of the object doesn't depend on how you observe it. Okay, so car traveling at 70 miles per hour, whether you're standing on the side of the road or whether you're riding in the car next to it, it's going to cover the same 70 miles in 1 hour, right? No matter how you measure it from either place. If you measure it standing still or if you measure it from the other car. And so that's what this means. The other thing that means is you can always break things up based on how they're observed. Okay, and it gets a little complicated there. Okay, but there's no real preferred way. Objects move the same way, no matter how you perceive their motion. Okay, the difference that the Einstein caveat that I mentioned has to do with light, but we probably won't get there. Okay, there are a few more practice questions this week in your assignment. I think there's something like 19. Use the examples in this section. Let me know if you have any questions. Shoot me that bonus question if you want to try to figure it out. You guys have a great week. If you need anything else, I will be around. And I will talk to you guys again next week.